want to talk about designs and get to the paired stuff. Now, design analysis is not new, we just know it today. Well, I guess that's not right when we get to paired stuff. But again, the analysis is even there. And then next up, I need to take a break for the correlation independence. So I can, from this I can back into regression. Regression actually we'll finish the course because that includes, well, it includes regression, but it includes all the, it's probably, that'll probably finish the course. Okay.
Is there going to be more text to download, more chapters?
I suppose so.
Can you slap something together?
I was buying my book, it's only $100.
Not done.
Yeah, we might have some. Now, design, look at two designs. The first is a completely randomized design. And we talked about the two sample problems, so I'll just put it in that context. In fact, that's the context for everything. For both designs. We do have two populations. Say X and Y. The other be the main variables. So we might have something like that. And then, of course, what we're after is this difference in means or medians. That's our target. Back to location. Okay. And now we want to talk about designs for inference on data. And the first design is the completely randomized design. Now you can think of X as control or treatment one, it doesn't really matter. Why don't we just use control and treatment? Bigger is better. So CRD is what? With a completely randomized design, CRD, we select n subjects from the reference population. Okay. So you might think of that as a reference population. And that's what you're selecting from. That's where you want to make your inference. On that population. And in many studies, There's a lot of discussion on what the reference population is. But once you have it, then you select at random. It should be at random. Dependent experimental units, but you, in a sense, you select n experimental units or subjects, okay? And then you randomly assign them. You want to control, yes, and two to treatment. In practice, you often take N1 equals. That's your most powerful design. You can show of all combination of sample size, this will give you the most powerful images. So, you often set off up doing that, but then maybe a unit dies or something, it goes away. So we end up with an unbalanced design. This is called a balanced design. Okay. Any questions on that? Then during the experimental time, the experiments. At the time before you take the measurements, all other variables remain fixed. Conditions don't change. Now, this is very hard to do when you're doing stuff with humans, so you try to do the best you can, and you may end up taking covariates because you know it's not going to be true, and you'll use those covariates to adjust your analysis, etc. And we'll talk about covariates later on. But that's what you try to do. I mean, if it's an animal experiment, that's why animal experiments are done. Then you can really keep things under control. Right? You want to keep all the other variables under control. If it's an experiment on animals, you have two groups of animals, and they have the same living conditions. Maybe it's a some kind of drug experiment, and you can mix that within their food. Then the animals have exactly the same food, all right? You try to keep everything under control. In fact, the animals you select from your reference population will be very similar, right? Usually they're experimental animals, and they will be very similar. The more similar, the better. Okay. And then if you want to do this study on humans, if you did it on animals, it'd probably be called a preclinical study. And when you do it on humans, it's often called a clinical study. Okay, then when you do it on humans, then it's hard to keep it again everything under control. But that's the design, right? And so then what do you end up with? What's the data coming out of the design? It's just two random samples. You have X's and you have Y's. These are independent. So that would be your data. And the target wouldn't be any difference, right? Just use the differences in these. and then you're after the target, and then let's just do like a Wilcoxon. So the analysis would be, yeah, it would be Wilcoxon, right? So you let, I'm copying down the notations so I have it right. You just rank the Y's, right? And then you reject each one. No, equal to 0, they will. The variance is W is too large. You know the expected value. The average rank is n plus 1 over 2, and they're in 2 lines. And the variance. Is that right? So you can calculate an asymptotic p-value, right? P would be the probability that W is greater than or equal to what you observe, right? You might use continuity correction. Then you can standardize and calculate. And then you, maybe it's the effect you're after, you can, the estimate is the median of the differences. And we have confidence level, right? Based on those order differences. Etc. Okay. I don't know. Let me see if I can. Let me see if this one comes. I'm not sure if I can get to that. No guarantee. I can go back. Oh, there's no guarantee this one. It did, okay, so this is just, I clicked on data on the web page and there's a bunch of data sets. Too quick.
Too quick. Too quick.
This is on the page. Anyways, in this experiment, this is an experiment on cholesterol compound for reducing LDL, low density cholesterol. And it's a study done on the quail. And this first group where there's ones here are the control, placebo. And the second group is the ones that got the drug. And it was a completely randomized design. This is actually part of it. So they randomly assigned 20 quail to placebo, that's what we think about here, and then 10 quail to drug compound. And then the experiment was done over 6 weeks, and during those 6 weeks, they were fed the same diet, but this one had the drug compound mixed in with this food. And LDL was bad, you wanted to reduce it. So that's the yes, it is indeed. No, okay, I got it. There are the measurements, right? So these are the combined. Okay? So definitely, what's the diagnostic comparison box plot? We could just use that. We could just do box plot. And then we'll split. And, the other one is and you could do this in Minitab too, right? Okay, now, the zeros are the treatment, right? And these are the final LDLs, and it looks like the treatment worked, right? Except for that guy out there, he had a huge outlier. And I worked on a lot of these data sets, and we would have outliers all the time. And, LDL is not the easiest thing to measure, especially 20 years ago. And it's probably 15 to 20 years old. And, so you had outliers on the right and sometimes on the left. But there's, it looks like there's a very clear break. So that would be a very good plot for this study, okay? And it looks like maybe the drug worked. And then I think we can use that indicator in the test, right? Not going to do it, I'm just going to do this. So there's my control placebo right in this. Okay. Then we could do a one-sided test or a two-sided. Why don't we just do two-sided? Then we would do the man-Whitney. We combine data and ranking, right? And then, of course, we use the computer. We're in R, so we just use what box test, right? Get the order, but we'll find out how to do it. And just break out some lines and so on. But I won't answer it. That's how you get the confidence of it. The test is not significant to two-sided. It's a poor printout. You have to figure out the mean and everything yourself. They should give you a z-score. They give you a p-value, okay? But we've done that, so we don't have to do this. I want it to be effective. Get that with. Yeah, the confidence will include 0. It's not significant, that's not surprising. And the difference is 13 point, almost 14 units. So that might be highly significant. If you did a one-sided test, it would be marginally significant.
And why wouldn't you do a one-sided test if you're looking for a lower Y?
Right, you could, right. I mean, that would be your hypothesis. Then you have margins. Okay. Background for this data, these were tests done on many drug compounds. It was a screening device the search was on, this is before Lipitor, okay? And the search was on for the drug to low cholesterol. So they looked at a lot of compounds, and you would probably ride with the higher alpha, because what you want to do is pick out the ones that look promising and then go back and look at them. Okay, it's better than old Upjohn, that's all it is. And Upjohn did have a cholesterol lowering drug, and it was on the market for quite a while. It wasn't a statin. But that's possible. I think it might even still be. Of course, Pfizer owns it, but. Any other questions on it? So that's an example of a completely randomized design and its analysis. This is probably, yes?
The one question I have is going back to the box plot, the middle 50% of the data on the lowered one, its IQR has expanded and includes the other
Right.
box. Can anything be said about that or any
You
kind
can
of
use the
conclusion?
finger clean test on this. I did this. Here's a long story I can go into on this one. But you can do the figure clean and it's not, you just don't have enough data to see. Well, you might worry about that. You can read about the study if you want. It's in, I wrote the paper up at the time, didn't want to. It's probably in different. Do I have enough the references? I think it's more and see what Okay, any others? That's a good question. The t-test is much worse. You can do a t-test on this. Now the p-value is 58%. The outlier, which you know. Okay, you can see the length of confidence intervals. The Wilcoxon goes from -3 to 26, and the t goes from -13 to 23. So that's much wider. And the estimate of the effect is
So the t-test
they must
isn't as
get 5, right?
so
They've estimated by 5, and if you look at the box plot, it's very close to 14. The estimate did a good job. It just didn't have enough data to have significance. I think the difference in mean is about 14, right? So that would be about 64 or so, and this would be 15, maybe a little less. So the box plot difference in medians is about 14 or 15 units. It's not 23. It's not 5 units in squares. That outlier here will be squares, right? If you could have the means on these plots and an outlier, it would boost the mean up to within 5 units. So the mean grows there. It's probably about the same on that.
So you
Okay.
could say that T is less precise than that
Oh, yeah, it's much less
Wilcoxon
precise.
in this case.
The main confidence interval is much longer. Any other questions? Okay, that's completely randomized design, and that extends for K samples. We'll use it when we do one-way ANOVA in this class. Again, the data may be observational. This was a designed experimentally. If the data are observational, then you still do the analysis, right? You just can't talk about cause and effect. Here you could start talking about cause and effect, right? Especially if this came out to be significant. Well, even at that level, it might still be in the next test. I was called in to consult on this problem because these experiments are usually done like with 15 drug compounds, one would be a placebo, 10 observations per each. And they do them very rapidly. When they get the data and have all these outliers, and then they do least squares methods, they were not getting significance. So that's why I ended up consulting on this problem. Hey, well, what I was saying, I mean, then you can start talking about cause and effect. See, this would be it's a difficult experiment for humans. You have to keep on the same line. So, probably 6 weeks isn't long enough for you. They use quail because quail seems to have the same problems with cholesterol as humans. Okay, now, so now on the second study, the design of the pair design. The villain offered in the CRD is noise is just too much noise to see the target clearly. So you want to look at noise reduction design. In a CRD, you have n pieces of information. Well, the setup remains the same. That's good, so we're not changing the setup. And in this case, you don't select subjects, you select n experimental units and divide them into. Okay. Now, first of all, how do you divide them into? That's the kicker here, okay? And that usually stops. I mean, you can't take the quill and divide it in two. That's the experimental unit. So if it's humans, you can take what? Identical twins. You have identical twins lying around. Then you can divide them into two. Or you can think of experiments like a good one is house paint. If you've ever painted the outside of a house, you only want to do it once in your entire life. So you want to paint the glass or something, or you might have some fall for the paint. And then you could pick on one wall and divide that into, you have two paints, like Sears and Britain. So that would be an experiment. Maybe you're doing some experiment on the strength of a cloth to use for clothing. And, you could take a piece of cloth, you could take 10 pieces of cloth, and then divide each of those into. Maybe some kind of stain, and just have the same piece of cloth, and you have to keep it separate. You can look on both sides of different solutions. Okay. And then what's the data coming in? The data actually comes in this way, right? There's nothing you can do about it. They're paired. In fact, you want them to be very highly correlated. So you're stuck with data like this. Again, these are usually very dependent. Okay. So that's your data. But the nice thing about it is, if you take D sub I to B, Y sub I minus X sub I, and the expected value of D sub I is the target. The same target, okay? So you have the same target using the D's. And I goes from 1 to n. Then the CRD in this context, the amount of information would be 2 times n. The amount of information in this pair design is n. So we've cut the amount of information in half. Okay. Well, I have an example here. I got this out of a psych book by Siegel. It's a twin data. And I think it might be real data. Siegel lived in the 40s and the 50s, and this is an example on preschool, all right? Probably nursery school. At that time, there weren't that many nursery schools, right? Well, I didn't know it. There were no kindergartens when I was a kid. I had to learn to read on my own, but certainly there weren't very many nursery schools. So this study is on identical twins. It took 8 identical twins and randomly assigned one to stay at home and the other to go to this nursery school. And then the response of interest was how socially aware they are, which is in the vote now, right? Okay. Now, before I get into that, I meant to say this before. You've also got one other thing regarding for you. When you do a randomized pair design, you set up symmetry under the null hypothesis. And that's easy to see, okay? So remember, it's randomly assigned within a pair. Okay? So, suppose H naught's true. There's no effect. Okay? Okay, so now you flip a coin. Here's the flip, all right? And then this is what you observe. If you flip heads, you observe, well, it doesn't really matter which, but just say you observe y minus x. That's your difference. And if you flip tail, there's no effect. You're going to observe x minus 1. And furthermore, both of those are equally likely, right? So this would be minus that. Right? So when you're looking at the distribution of these, here you observe y minus x, here you observe x minus y, and it's just on a flip of a coin. So these have to be equally likely. The d's are symmetric about 0. They have to be, right? Because there's no effect going on. It's just that you, one time you flip the head, the next time you flip the tail. Okay? What you measure stays the same because there's no effect. So under H9, these are symmetric about 0. So the worry about, okay, I'm going to use a sign rank Wilcox and I have to have symmetric errors is over, right? You can use it because under H9 it is symmetric. Under alternatives it might not be, but if you're looking at a small effect, it probably will be. Just do the sign rank Wilcox one, and it's C+, right? Okay, so there you can, it's one-sided out. Then you do your p-value, you can be able to have some individual challenges. Any questions on that? So here's the data. Sort of like this data. You know, when you have small kids, they're different, right? Even their siblings are different. Now, after 12 years of school, they're all the same. But at the beginning, I don't think they are. This one's, you can see a lot of difference. This is the social awareness test. So there's the data. And the one first pair of twins, the one that went to school scored at 82, and the one that stayed home scored 63. But you can see even those, those that went to school, like number 4, there's like a 40 unit change between it and number 1. Right? So there's a lot of range in the data. And that would be like data, and it's about the same range for the one that stayed at home, because there's a 42 and an 80. So there's a lot of variation down through the data. But the pair differences, you don't look down through, you look across. And then that's the differences. You can see when you go across, I don't know if I print out the differences. Here's the box. Okay, so we could do this on that one. Let's get it in. I could just type it.
Um, just skip it first.
I'll go through. And then we're just going to form differences. So if we leave it like that, or have to call them out sometime. Y should be second column, right? That's the one that went to school. And next should be the third column. That's the one that's and then if you're doing a 2-sample problem, that's how you would look at the data, right? And so your range would be 40 units, right? Today, you're amazing data. That was 40 units too. So there's a lot of noise in the data. But we're looking at D, which is just Y minus X. So those are our differences. And there's what, about 30. That noise quite a bit. That's the beauty of the variable zone. Okay. So then the analysis would just be the sign rank Wilcox model, right? So we could do it's the same command, just put in the D's. And then that would not So for a two-sided test, it is significantly above 5%. Effect size is about 7. I don't know if that would be important or not. Okay, send your kid to nursery school. The first child we had, we sent her to nursery school and then she quit. She came home one day and now she doesn't ever remember it back again. And we decided not to push it to that time. So she had to go to kindergarten. Okay, now, suppose you did the wrong analysis. If you do the two-sample analysis on it, it's the wrong analysis because the x's and y's are not dependent. You can plot see there's some correlation. It's not that strong, but there's some. You want positive correlation, if you think about it. If it's negative correlation, you've done the wrong thing, right? You don't want negative correlation in this design. There's another data set, I don't know if it's in the book or not, it's the Darwin data. And if you look at that, it's not negative, but it's not very strong. Talking to Caucus. But if you accidentally do the wrong analysis, see, the Caucus will just include zero. See, look how wide the confidence interval is. Even the effect is a bit minus. And the p-value is 25%. That's we would do on one. That's a two-sided test. So we probably do a one-sided test. It would be significant on one side. You know, the p-value would be 20 over 30. So you would ring a bell on the side. Here you won't. 12%. Even though this one has more information, in this case I think there are 8 twins, 8 units. So, this analysis has 16 pieces of information, the other one only had 8. But it really cut the noise down, and it was much more simple. Again, the second analysis is the wrong analysis. It's not correct. Any questions on that? It's hard to do a pure design. I mean, you have to have those experimental units. And you have to be very careful in matching. You will find studies where they try to match people and like on IQ or something before they do it. You know, if you had identical twins, that would be a no-brainer, right? They have almost the same IQ, right? And again, they have exactly the same environment. So there's a no-brainer with identical twins. It's a perfect unit. But then you might do a study and you match them on IQ or something, and that's very dangerous. If it's identical twins, then they have the same work, probably the same motivation for working. But if you take 2 people and match them on IQ, that's a big wish. Then you try to do a lot of matching. There are studies that do that. There's quasi-experimental designs where you have this huge observational study, and then you try to do matching based on covariance. I've done some work with Bad Heidemann and Psych on that. It's called propensity analysis. That's a scheme we use to do that match. But it's still not as good as a complete randomized pure design. Now, if you don't do the randomizing, then you might not have symmetry, so you have to be careful with that. Those studies are like before and after studies. I mean, you can't change. Often in a clinical study, we try to use the same subject as treatment and control. It could be before and after, but sometimes whenever you give the patient a washout in time, you have like a washout period, and then you have what's called a crossover design. So we use these designs quite a bit. Okay, so then, again, the next things we're talking about in this class are serial regression, at least as a background. If you're looking at paired data and they're both discrete, then you can test for independence. And this is independence, right? You can test that in a very natural way, especially if you don't, if the ranges are sort of small. If they're large, then you might end up with a sparse table. You have to be very careful. But, you know, like hair color and eye color, that's it. You just put that in a contingency table. Okay. So your schematic is just this. This would be a probability model. You have the range values of y here. C columns, and range values of x is here, and this one for reference. And you're trying to check this, and that just tells you, you know, here's the probability x is equal to x1 that's sitting in the margin. Talking about that, and here's a probability that y is equal to y1 that's sitting in the and independence says if you multiply these two together, okay, you should get this thing in the cell. That's all independence is, right? Now, in real life, you don't know the probability model, but then you just collect data and you just put it in the C table. It looks just like that, okay? And then you can do a chi-squared test for independence, right? You know what you observe, and then you know how to compute the expected under independence. You just collect the data in the C table. Your rows, right, the observed frequencies. The EIJ is under independence. And then the test was what else? One of the oldest tests known to man, right? O minus C squared over E. And then reject independence. That's where it's in there. Right? Well, I don't think we talked about this. I don't know if we got that far.
Are you comparing it against the chi-square with 1 degree of freedom at your significance level?
No, your screen will be the number of rows minus 1,000. We could talk a little bit about the expected value. That would be the expected frequency in the IJ cell, right? You just need to know that, and then just what is under independence. Now, you don't know those probabilities, right? If you did, then you wouldn't have to do this test. But you can estimate those. Those are just in the margins of the table. And they're the non-parametric estimates of those probabilities. What else would you do? Even if you're not thinking about independence, and I told you, here's some data. I've got them in these C table, but I want to know the probability X is 4. What's an estimate of it? You would just go down to row 4 and then add up those frequencies, right? And that would be that probability. In other words, you would just do this, right? It would be a number of row I. If I ask you what's the probability that X is equal to this value, and you would just add up those probabilities, and in the C table, you would just add up those frequencies and divide by that. And then this would be the number in the column J, right? And when the ends cancel out, and you got the row total times column total, and the total number. So the expected frequency is easy to get. The rest of you did right. Then your degrees of freedom, you collect this data, and if you have all the cells in, and you don't know the last one, because you know the total sample size, I can give you the count for the last cell. Right? So there are like R times C minus 1 free cells at the beginning, but then you had to make how many estimates? You had to make R minus 1 here, and you had to make C minus 1 here. So you have to subtract off your estimates. And when you do, then put things back together again, you'll get R minus 1 times C minus 1. And then I think in the book, yeah, oh, no, that's good. Any questions on it? You can, there's some examples in the exercises. It's just like, in Minitab, you could just type in the C table just as it is, say in columns 1 through 5 maybe, and then you can just do CHIS, C1 dash C5. And you can get that clicking too. And that'll give you the chi-squared analysis. In fact, Minitab does give you a very good chi-squared analysis without any, without turning on many things, unlike R. R doesn't do so good on this. You can get the table together, you get table in R, and it's, I think it's, chi-squared dot test, and then table. And it's called map. How about C table? But then you turn on things where, with additional functions, you can get residuals and things like that. We'll go over a few examples next time. But getting back to our story, now, what if you wanted to do this with continuous data? Then you're out of luck, right? Because you don't have. This all depends on the discrete probability model, which you don't have with continuous data. You won't be looking at probabilities like that. In fact, with continuous data, the left side's 0 and the right side's 0. All right. So then what do? I mean, you take low, measure, for that x, you go x plus delta x or something. And then what's delta x? That'll depend on who's doing it, right? Try to make it a grid, but it's kind of dumb. So you don't have a natural, this is really a non-parametric test for independence. It doesn't matter what discrete model you give me, I can run it through this. The only hang-up will be if I have a lot of categories and I have a sparse C table. And you'll get a warning message when you do a chi-squared test, either with Minitab or R.
Is this also used with categorical data, with counts and so on inside that contingency table?
Right, you can do it with that too. So let's talk a little bit about the continuous case. This upsets a lot of people, at least in the old days. You read papers about someone trying to finally figure out you've got a parameter, measures independence. Yeah. You can't do it in a continuous case, so if you can't do something, you do an end run, right? You can't go up the middle like you could with discrete, so we're going to do an end run, and then we change the rules, maybe not change the rules, but we decide to try to measure something else. Okay. So again, now you still collect this data. This appears. But now you can't go into a C table. There's no way to do that. So, but you do have paired data, and then you, what would you do? See, the C table is natural. I don't know what else you would do with category data. How about continuous data? What would you do? What's the next step here? Now you want to see you're collecting pairs of continuous measurements, and you want to see if they're dependent. Maybe here's a dumb example, X is height, Y is weight. Is there a dependence between height and weight? Here's one, sort of true, right? Yeah, for sure people. Y is income, X is height. Right? There's an increase in relationship. Seems to be anyways. And you can think of many more. Baseball players, X is weight, Y is number of home runs. Well, that would be, well, you treat number of home runs up. I think it's- There's no discrete analog, but you are interested in the relationship. So you, what? What do you do for the data?
R squared.
I give you 10,000 data points.
Compare the distributions.
Well, no, you're not really, you want the relationship. You don't want to look at the distribution. You want the relationship. If X is big, is Y big? If X is low, is Y low? You want to do what?
R squared.
You're getting ahead of the game. Just scatter plot the data. Okay, so let's finish with this plot. It's a nice plot. Give you the height, but they don't give you the weight. So you want to plot. X would be height. Y. There's a lot of noise in the data. I mean, here's people who are 6'1", right? And one guy weighs 160, and another guy weighs 220 pounds. So there's a lot of variation, but there definitely is a trend. The trend's up, right? As height increases, weight increases in general. Okay, not for everyone, okay? But there's a trend, and you're after the trend. Okay? So you can even start thinking about what you want to measure. If we want to measure the relationship, we'll do that next time. But you can start thinking of the slope, right? If you play around with a few numbers here, you'll see the slope's about 5 in this data set, so it's 5 pounds for every inch. That's regression, okay? And that, we definitely want to be talking about that probably within a week. Maybe even on Thursday. You want to just look at relationship now. And I claim there's an easy way, I can't write on the screen. So I have a data set like that. And I might not be able to measure independence. I really might. those two lines, I can measure linear relationship. There's many more data points in these two quadrants than in these two. So what, the continuous data, we change the game. We don't talk about independence. We talk about relationship, and we try to measure. The first one we'll look at is Pearson's R. The traditional one, it tries to measure linear relationship. And then we'll do Spearman's and Kendrick's. And then we can do it. So Lauren, there's no quiz on Thursday.
What?
Closing homeworks.